Hello, dear colleagues, and we will take a deeper look in construction of a patient trait matrix, which is the basics of all subsequent analysis today. And let's start with objectives for today topic, and we will try to identify case steps in transforming messy clinical data into tabular form used in machine learning. List some of the factors and determine the decision to include or exclude a feature. We will describe what is meant by missing data and explain how to fix it. We will describe the purpose of feature construction, define the knowledge graph, what is knowledge graph, and give an example for this structure. We will explain how to use knowledge graph and how it can help the data analysis in clinical data. Patient feature matrix contains patient data in tabular format. The data for a specific patient occupies a single line. Each column represents a separate dimension or characteristics. In clinical trials, the unit of observation and analysis is almost always the patient. In a data frame, each row contains all the data for a single patient. Each column contains a different characteristics. Once we have decided on the unit of observation and analysis, we move on to determine which features to extract from the data. It's best to start with all the available signs. If there is a computer source limitation, you may need to remove features in order to reduce the size of the dataset. Some modern machine learning techniques can automatically remove these features that have the least impact on the accuracy of the model. It's important in order to ensure patient privacy as well as comply with personal data laws, so you will need to remove sensitive patient features. We can use implicit information hidden in the data to help us create features. Metadata is a means of classifying, organizing, and characterizing data. To put it simply, it's data about other data. Metadata can be very informative. For example, we need to determine who has diabetes. Identify, we would look to do so, we will need to look at the results of such as glycated hemoglobin tests. However, we can also use a number of orders for lab tests that have something to do with glucose measurement instead of the actual results of these tests. So we used metadata number of time a glucose test was ordered, as well as some prior knowledge that diabetes is a disease in which glucose levels are confused to create a trait percentage of glucose related tests that tell us whether a certain person has diabetes or not. Usually, such features are created or constructed using some prior knowledge. Such features can also be explored using calculations. As you learned earlier, healthcare data can be either structured or unstructured. Steps to take when creating datasets from structured sources will be assess to this structured data, feature normalization, reduction the number of features, dealing with missing data, creating new characteristics. So let's take a closer look at all the steps in this sequence. Structured data is typically stored in database tables. Data manipulation languages are being used for data queries. The most common language here will be structured query language, SQL. Results of the query can be uploaded to analytical systems. Data in different tables can be linked to each other using data modeling mechanisms. If there is a relationship, data from different tables can be retrieved in a single special kind of query. So in some cases, we may need to convert the data from one format to another that's more suitable for use in this exactly research. Distinction should be made between the concepts of normalization and norming. Normalization is adjustment of values according to some transformation functions. The purpose of normalization is to make the data more convenient for comparison. For example, by reducing the data to a single unit of measurement, data normalization is required for datasets which are using heterogeneous, incomparable units of measurement, or there is a need to express some values in some understandable units of measurements. For example, the response time in milliseconds will be easier to interpret that number of processor cycles. Standardization is the process of establishing maximum permissible or optimal normative values in applied areas of activity. Standards can be developed based on the results of research or scientific work, or on the basis of expert assessments. The need for normalization is caused by the fact that the scales of the values of different data characteristics can be changed in different ranges. For example, age will vary from 0 to 120, income ranging from 0 to several hundred thousands or even millions, white blood cells count in the hundreds or millions. That's the range of change in the traits, age, income, and leukocyte count differ by thousands and millions of times. When analyzing this kind of data with machine learning methods, this imbalance between input variables representation at different scales has an impact on the estimation of the dependence between these variables. At the same time, the impact is not due to the real dependencies, but to the different scales of these dimensions of data. As a result, the trained model can identify individual or missing dependencies. In this way, normalization facilitates subsequent analysis by reducing the impact of extremely large or extremely small values compared to other values in the dataset. Transformation used in this example is called minimax normalization. This normalization method scales the values of each column to that all values go between 0 and 1. A generalized variant of minimax normalization with reduction to a range of values. Another common normalization method is dimensional scaling. It consists in moving the decimal point by the number of digits corresponding to the order of the number. When this number in the largest observation value, so we'll use it as a scale. Another method on normalization is mean normalization or Z normalization. The disadvantage of minimax normalization is the presence of anomalies in data values. This data stretches the range, and as a result, the normalized values are concentrated in some narrow range near zero. We can avoid this by defining the range of values through the minimum, maximum, and through the mean variance. The values obtained by the formula are called z-scores in statistics. Another action when creating datasets from structured sources is to reduce the number of features. Often the datasets you have to work with contain a large number of features, the number of which can reach several hundreds or even thousands. When building a machine learning model, it's not always clear which of these features are really important. So we will need to have a connection to the target variable and to define if this variable is important or not. And others will be just noise, which we don't need to analyze. So removing redundant features allow you to better understand the data as well as reduce model setup time. It will improve model accuracy and make it easier to interpret. In general, feature selection methods are usually divided into three categories: filter methods, embedded methods, and wrapper methods. We choose to the appropriate method it's not always obvious how to do it. And it will depend on the task and the available data. Why might this be necessary? Some of the signs may be not helpful. For example, absence, the sign may be absent in most patients. Rare, this patient lack a large number of signs. Redundancy, trait 1 can be highly correlated with the trait 2. Speed, a large number of features can slow down the analysis. Confidentiality, keeping more features increased the likelihood of a patient privacy breach. Characteristics with low prevalence and low variance are suitable candidates for removal. One of the ways to reduce the number of features is to combine or aggregate the features. This action is actually done on the basis of domain of knowledge. The advantage of this aggregation is that it can eliminate some of the coding features of individual clinics, making it easier to make cross-clinical comparisons. The aggregation phases require an accurate representation of domain knowledge in the form of knowledge graphs. There is a wide range of mathematical techniques to detect and explore patterns in data. For example, the principal component analysis or PCA is a method which is based on the fundamental mathematical apparatus to analyze these characteristics. The advances of using machine learning mathematical methods are that they are not subject specific and do not depend on specific medical knowledge. Of course, there are also drawbacks in the mathematical combination of existing features. The main one is that it makes it difficult to interpret the derived traits. A derived set of features may also allow us to accurately predict what we should understand through this analysis. But the feature contribution to such a prognosis may not have a clear clinical interpretation. There are some other things to keep in mind when we are planning to reduce the number of signs. Analyze whether differences reflected in the trait of relevant of your research question. Keep in mind that the more flexible the model you are using later in the analysis, the less useful aggregation will be. Aggregations will not do more good than gradient boosting trees, reducing the compute footprint required as a benefit regardless of which model you choose. After transferring patient's data into the timeline to the patient feature matrix, some cells in the matrix are empty. So, what do you do with the missing data? In prospective studies, the lack of value in the data item suggests that it wasn't recorded. But the data wasn't entered for some reason. However, when we talk about data that is byproduct of everyday care, the presence of free space in the patient's feature we introduced doesn't mean that this value had to be recorded by anyone. So in some cases these features will be or will not be presented. The absence of a specific value in the column of the patient feature matrix can mean that certain events have happened. The value should have existed, but it is missing. Collection error related to collection error, data migration errors, and other reasons. The missing value is an artifact of accepting a tabular representation of the data. The value may have existed but was deemed unnecessary to collect. Two key problems with the lack of data in the analysis are how do I show the system that data is missing. If the data is indeed in the category of missing data, how is it calculated? Some systems allow you to use special data elements when writing an non-available or missing value to represent a missing value. Other systems may use numeric values that are outside the range of possible values for this function, such as 0 or minus 999, to indicate a missing value. You can, of course, simply delete patient records with missing values. It's a tempting and simple solution, but it often creates problems. Deleting patients with missing values is likely to result in a lack of patient representation in dataset. This would potentially skew the analysis. One widely used method in the imputation of missing means missing values will be imputation, the kind of prediction that files in the missing value based on other information in the dataset. The simplest method of inputting data is called average imputation. It consists of replacing the missing value with the average of the known values in the same column. This assumes that the value of the variable in the other rows in this column contain information about the missing value, which is most often incorrect in medicine. To improve the imputation procedure, we can use values in other columns of the same patient. This is better than inputting a value which only takes into account the values in that column. We use the expected correlation between different characteristics of the same patient to infer the significance of the missing characteristic. The procedure is called K-nearest neighbor imputation. It will help us to fill a missing cell by looking for patients who are similar to the current patient in other ways and then use those known values to impute in the missing cell. A modern technique called multiple imputation repeatedly invokes imputation to create multiple versions of data that can be analyzed to arrive at the estimate of the variance of imputed values. So let's talk about how to make decisions to remove missing values or impute them. If the trait value is most often fixed and a small portion of the data in the sample doesn't have this value, you should consider imputation. If the value of a particular trait are largely absent, it's worth considering excluding this trait, since the trait isn't informative for the most patients. So we will have to impute values for the most of the patients, and it's not a good idea. If the distribution of missing values is in the middle zone between these alternatives, some experts will advise adding indicator values to mark which values have been imputed. But this recommendation has been challenged by others. For a particular point of view, it's probably better to use an analysis method that naturally handles missing values rather than necessarily imputing them. Finally, you should consider how important the missing data feature is, and could you avoid imputation by answering the question without taking this value into account? By converting the presentation of patient data on the timeline into a patient feature matrix, we can also perform simple operations on the source data to create new features. This construction of new features is called feature construction. Constructed features are the result of transformations of the original elements or their combinations. Simple models with elaborate features can perform better than indicate models with original features. Clinical scoring systems, simple formulas that combine values found in EHR are excellent examples of constructed features. Body mass index is a relatively simple example of a point system that allows to assess the severity of someone who is overweight or underweight. Other assessment systems to quantify the total burden of multiple diseases, often referred to as a burden of comorbidity, and comorbidity from the Latin of together, Morbius disease alignment is the coexistence of two or more diseases, syndromes, or mental disorders in one patient, interconnected by a single pathologic mechanism, or they are just coexisting in time. Typically, such scoring systems are used to account for a patient's overall illnesses in analysis and to prevent comparing sick people with healthy people. Other examples include creating proxy features for the patient, socioeconomic status based on their zip code and the number of HR records they have, or scaled by overall health and other types of data generation. General tips for constructing features are: consider which traits may be significant but not directly measured by advantage or pre-validated clinical assessment systems. When creating new characteristics, take into account quantity differences, changes over time, and rations of existing dimensions. Strive to create new features using clinical knowledge and creativity. Strike a balance between the benefits of creating new features and the effort that goes into creating them. An alternative to creating new features could be the use of deep learning methods. Deep learning is a machine learning method that uses more than the usual amount of raw data and creates the necessary features without domain knowledge. And deep learning is characterized as a class of machine learning algorithms which use a multi-layer system of non-linear filters to extract features with transformations. Each successive layer receives the output of the previous layer as input in the system. A deep learning system can combine supervised and unsupervised learning algorithms with sample analysis representing unsupervised learning and classification representing supervised learning. It has several layers of identifying features or parameters of data representation. At the same time, the characteristics are organized hierarchically. The characteristics of a higher level are derived from the characteristics of the lower level. It's a broader field of machine learning exploring representations of data. How to build layers of multiple level of representations that correspond to the different levels of abstractions. The layers from a hierarchy of concepts. Bottom line will be when creating out-of-the-box datasets for analysis of the data on patient data, you should keep in mind that structured data in database tables can be transformed into analysis-ready datasets called the patient feature matrix. At the same time, the number of features in the patient's feature matrix can be reduced by aggregating features using domain knowledge or by using mathematical methods such as principal components analysis. Missing data can be deleted or inputted with varying levels of methodological complexity. When building an analytical system, you should consider the possibility of creating additional features from the source data or the applicably using deep learning methods in certain cases. And a knowledge graph is a declaration of the entities that exist in domain and the relationships between them. This is also called ontology. Ideally presented with digital solutions, it will be structured as a tree structure. A common problem when working with the clinical data is that there are multiple ways to express the same concept. Knowledge graphs can help because they explicitly represent entity, symptoms, and relationships between different entities. So, what are the knowledge graphs? So, what exactly is the structures? Knowledge graphs are made up of entities. There are sets of equivalent names, synonyms for the entities. There are relationships between these entities. A very common attitude will be species. The kind of relationships in knowledge graphs is most important because it codifies what is the type and of a certain medical field. These entities inherit properties from the entities of which they are a variant. Knowledge graphs can contain links to other knowledge graphs. This can provide a consistent way to reference entities from different data sources. Knowledge graphs are extremely useful when querying clinical data. They help identify different terms with the same meaning. In medicine and biological research, hundreds of knowledge graphs are available. And they are easy to find on the web. For example, it could be Bioportal, Center of Disease Classification, RX Norm, Anatomical and Therapeutic Chemical Classification System, and also, you should notice unified medical language system, which will try to standardize more than 140 knowledge graphs in this area of knowledge. Let's finalize with the following questionnaire, which can be used to assess the knowledge graphs. What entities does a knowledge graph contain, and what is the basis for classification? What words are used to denote objects in a graph? Are there synonyms and alternative names? Does it make a map of other knowledge graphs with outgoing connections? How related is a knowledge graph to other knowledge graphs? In addition to these fundamental questions, there are several practical approaches to assessing the knowledge graph. For example, given the data from the EHR, the number of terms from each knowledge graph that are mentioned in the EHR text document is counted. Alternatively, if the knowledge graph is too large to include million terms, you can use term occurrence counting to decide which terms to keep in mind. Those knowledge graphs are large, carefully selected collections of medical objects, alternative names for objects, and the relationships between them. They are extremely important source of medical knowledge for feature creation and clinical text processing. For today, it's all. Thank you very much.